Good morning, everyone. My name is Eric Romo. I am the business statistics tutor here at Fresno City College, and today we'll be talking about hypothesis testing. Now, this area of statistics usually gets people a little thrown off course, but just follow along as best as you can, and I hope to clarify what's really going on and maybe give you some pointers on how to tackle a couple of these problems. So I think the best way today is to look at an example problem and work it out together as I explain the concept. So let's go ahead and set up my stuff real quick. All right, foreground. Okay, so let's take a look at the situation. A leading manufacturer of trash bags would like to know if a new prototype of a 30-gallon bag is stronger than their current 30-gallon bag. The current bag can hold up to an average of 50 pounds with with a standard deviation of 1.65 pounds. After sampling the 40 prototypes of the new bag, the average of the samples was found to be 50.575 pounds. Conduct an experiment to determine if the manufacturer should implement the new bag into production. Okay, so let's start thinking like scientists, specifically data scientists. So a hypothesis, okay, is a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. A theory, on the other hand, is a supposition or system of ideas intended to explain something, especially one based on general principles, independent of the thing to be explained. So, when you hear somebody say, I have a theory on why there's so much traffic in Fresno, well, they don't really have a theory, it's more of actually a hypothesis that they have. It's more of a claim. Because a theory is usually a system of hypotheses, multiple working hypotheses that have been tested over and over and over again, and there's overwhelming evidence that we have accepted the theory as fact. So in statistical hypothesis specifically, is that we have what's called a null hypothesis or the alternative or research hypothesis. The null hypothesis is the statement being tested. You should treat the null hypothesis to be the statement of no effect or no difference. The null hypothesis is not rejected unless there is convincing sample evidence that is false. We replace the population mean we are testing against as the null mean right here. And we'll get into that in just a second. So our hypothesis alternative or research hypothesis is the statement that will be accepted only if there's convincing sample evidence that it is true. So what you'll hear in class is, okay, do we reject the null hypothesis or accept it? Well, the way I like to think about it is back to this whole start thinking like a scientist. It's easier to try and disprove a claim than to try and prove a claim. And the reason why it's easier to do that is because there's so many loads of evidence to try and contradict our hypothesis that it's easier to try and say, okay, I hypothesize that the traffic is due to so many cars coming on from the Shaw exit here in Fresno. Well, I can disprove that by saying, well, no, there's more traffic because it's more cars are coming in on average from Shields Avenue. So there we can re-evaluate our hypothesis and retest again. So if we look here, okay, I want to make a hypothesis, okay, from this example problem. I need a null hypothesis, okay, and I need an alternative hypothesis. So the leading manufacturer of trash bags would like to know if a new prototype of a 30-gallon bag is stronger than their current 30-gallon bag. Okay, so really, my claim here, so the claim is always given, okay? So the new trash bag is stronger. The new trash bag is not stronger. So notice the difference between these two. So this was the given statement to us. The new trash bag is stronger. And that's what he wants to know. Is the new bag stronger than the old bag? And here, remember that the null hypothesis is the statement of no effect or no difference. The new trash bag is not stronger. Okay, so also, what else did they give us? They gave us a population mean of the old, so the current bag can hold up to an average of 50 pounds, can hold up to, which means that our null hypothesis mean, okay, is less than or equal to 50, which means that we want to get higher than that. So what's the opposite of this is that our mean is greater than 50. So here, for the alternative, okay, versus the null, if I get a mean of the new prototypes that is less than or equal to 50, then I know that the bag is not stronger. It's either the same strength or it's weaker. Or if I get a mean that is higher than 50, which is 51, 52, or higher than that, then I know that the new trash bag is stronger, okay? Well, let's take a look. It said that the average of the samples was found to be 50.575. And to us, we'd say, wait a minute, that is stronger than the 50 pounds because 50.575 is technically, yes, it's stronger than the current bag. But here's the issue, is that in statistics is that, back to those confidence intervals, is how confident are we in making that statement? And that's what we have to test. That's why this is called hypothesis testing. How confident are we about those statements? Okay, so let's go ahead and talk a little bit more. So type 1 and type 2 errors. Okay, so this is important because a type 1 or alpha error is the type of error we made when we reject the null hypothesis when it is true. We usually denote this as a level of significance, alpha. And then type 2 or beta error is the type of error made when we do not reject the null hypothesis when it is false. So the higher the alpha error, the lower the beta error, and vice versa. The lower the alpha error, the higher the beta error. Therefore, we must always specify a level of significance before testing. So, one thing that I will add to this problem is level of significance is 0.05. Okay, so that's our alpha. So right away in my paper, I should write this right here, which is alpha is equal to 0.05. Okay, so that's my level of significance. Okay, so that's the probability of me making an error. Okay, now determine a decision rule. Depending on the level of significance, we can determine the z-statistic to test the hypothesis. So first step, decide whether we are trying to get greater than, less than, or not equal to. So, level of significance, alpha, is 0.05. Alright, so that's important to us because we need to determine a z-statistic to test the hypothesis. So what does that mean? Well, If I'm trying to get greater than my null mean, then that means that I'm doing what's called a right tail test. So if we look on the graph, okay, I'm going to have my normally distributed curve. Here's my mean, correct? Now, I wanted to get greater than, which means I'm going to be over here in the right tail of my graph, which over here, my level of significance is this area that I'm shading is 0.05, which means that I need to determine what this interval right here is. Well, if this whole thing adds up to 1, and I do 1 minus 0.05, this is actually 0.95. So, what is the z-score that gives me that area? Well, if I look into my charts, okay, I will find on my second step determining the z-values of your experiment. If greater than the right tail test, the null mean, okay, so 0.05, that's my level of significance, then z is equal to 1.645. Alright, so if that's true, then that means I need to go ahead and write that in. So my z right here, z is equal to 1.645, positive, okay? If it was different, like a left tail, then I would have used a negative. If it was not equal to, then I would divide my alpha by 2, 0.05 divided by 2, which is equal to 0.025, and distribute it evenly between both sides. So see here we got different z-scores, so plus or minus, okay? It depends on your situation, essentially. So here, see, the third to complete the statement with rejecting the null hypothesis, okay, so determining this decision rule. So we chose greater than, so right tail test. So if greater than the null mean z equal to 1.645, then reject the null hypothesis, okay? So in here, I'm going to expand this. I'm going to write underneath, right here, which is going to be ds, which is decision rule, or dr, decision rule, if z is greater than 1.645, then reject the null hypothesis. Okay, so from here, I'm going to need to do some testing, okay? So testing the sample evidence. We must first identify our sample space, the mean of the sample, the standard deviation of the population, and the null mean. And we simply plug in our values for the equation. So if this is my equation, I'm going to pop that in right there. Mouse this over. Alright, so I'm going to need z is equal to x bar minus my null mean divided by my standard deviation square root of n. Remember, standard error, this should all look familiar from our previous chapters. Okay, so what do I know? Let's see. Well, I know that my mu null is equal to 50 because that's the current bag, right? That's what we said in our statement. Okay, 50. I know that my sample mean of the prototypes we found 50.575. If you want to go back to the example here, maybe you can see more of what I'm talking about. Okay. And so also I have a standard deviation of the population which was 1.65, okay, and n we found was going to be 40, okay, so 40. All I have to do is plug it in and solve. So I should get 50.575 minus 50 divided by 1.65 divided by the square root of 40. Okay, so I should get, after calculating this out, my z-score should equal 2.20. Okay, so now this is where our decision rule comes in. So we ran the experiment. We are now testing the sample evidence against the null mean, and we have found that our z-score is 2.2. Looking at my decision rule right here, if z is greater than 1.645, reject the null hypothesis. Well, I just have found my z-score for testing was 2.20. Okay, with the corresponding p-value of 0.0139. So, from there, I can say, reject this. The new trash bag is indeed stronger than the old trash bag. Okay? So, now that we've done this, comparing the z-score to the hypothesis. Follow the rule you made. Reject or accept the null hypothesis based on the data calculated. Also, the p-value of your experiment tells you how convincing your evidence really is, especially if the p-value is less than alpha. Then interpret the statistical results. So this is basically our final step. Well, some of you are wondering, well, how did I get this 0.0139? Well, actually, if you look into your z-scores, okay, the z-score, which is equal to 2.20, okay, in the z-charts, has the area of 0.9861. And if I am in this area, then I need to minus that from 1.9861, which is equal to 0.0139. Now, like I said before, if this is less than this, which is, this is our level of significance, alpha, then I have what is called strong evidence that the null hypothesis is false. And that's all there is to it.